Jenkins. He's going to tell us about superselection sectors for stacked system.
Yeah, thank you very much. Of course, I would like to thank the organizers very much for the invitation to give a talk here. It's very good to be back here at ICMS. Right, yeah, so I gave a talk at Open Wolfvak maybe 2 months ago. I think many of people in the audience were there as well. I wanted to talk about 2 different things there. I didn't have the time to talk about the second thing. So now I do have the time. So in a sense, this is part 2, but I will start from start from the beginning for those who weren't there. I should first say, so this is still work in progress. It should be finished soon. Been saying for a while it should be finished soon, but now it will really be soon. It's joined with Sven Bachman in Vancouver, Alan Getz, also in Vancouver, and my student Naomi Ray. And really, so Alan is a PhD student of Sven, and really Alan and Naomi did most of the work. Yeah, so what I'm going to talk about, maybe I should also say this now, it's very similar to some results in the conformal field theory. So people with conformal nets, they will be surprised by what I'm going to tell about today, but we work in a slightly different setting, so we have to adapt some of the techniques. But yeah, maybe you want to start sort of with the motivation. So, I mean, in general, I'm interested in the study of in the classification of gapped phases of matter, so quantum phases of matter, a gapped ground state. So really what Yoshiko was talking about earlier. And in particular, I'm interested in these models that are called topology ordered, where we have these anyons. But this particular project is motivated, at least in part, by these invertible phases that we heard earlier about this week in Yusuke's talk. So, so the idea, just I will go into more detail about this later. But the idea about these invertible phases is that, well, we have, let's say, 2 states, and we have some product operations, which I will note by this. And this is should be something like trivial. All right, so that was more or less the definition of invertible phase. And so what you can find in the literature, these invertible phases, they should not have any anyons. And that was kind of like the motivation for us to kind of prove this in the setting of DHR theory. So yeah, that was sort of motivation, but our result is a little bit more general. Right. So that's yeah. So that's about the motivation. So let me maybe briefly say what the setup is that we're working in. So it's very similar to what Yoshiko about earlier. So I'm not going to work in 2D. Doesn't really matter. So for simplicity, we can just think of some discrete lattice, Z2. And so the sides are going to be called gamma. So it doesn't really have to be Z2, it's easier to draw. And then, of course, what you do, you take a finite set and you assign to this an algebra of observable. And for us, this is going to be this some quantum speed system. Right. And of course, this is, well, let me not write down these axioms, because you all know them, but this gives a local net of observables, and we can define our observable algebra, our quasi-local algebra, as just this thing. This is fine. Right, so that's our setup. That we're going to work with later. So, as I said, I'm interested in this classification of well, gapped quantum phase of matter. So I should define what I mean with a phase. So we consider states on A, and so it depends a bit on what you're interested in, but we're typically interested in certain classes of states. So typically, they're ground states of gapped Hamiltonians. So we have some dynamics. So in the Hamiltonian, this Hamiltonian has a spectral gap, and this is an interesting class of states. And I'm going to say that two states are equivalent if and only if I can relate them by some automorphism where alpha is here going to be a bit vague, really local. So really, what this means in practice, it's kind of like dictated by how willing you are to do analysis. So if you don't like analysis at all, you take something like this QCAs that queries that have kind of like strict locality. You're into Robinson bounds. You can relax this a little bit, and you can allow some exponential tails, for example. But really, the idea you should think of, you have some finite part of your system, you have some observable there, and then if I apply alpha, it ends up in some bigger thing. Maybe up to some error that goes to zero fast enough. That's kind of the idea. So why is this sort of also physically interesting? So how do we get actually these alpha? That's maybe an important physical question. So it turns out that for these topologically ordered models that we are interested in the end, the spectral gap is stable. So you can add if you add perturbations to it that are kind of small enough, the spectral gap stays open. You can relate the ground state of the perturbed Hamiltonian with the original Hamiltonian precisely by such a quasi-local. So really that's one way of getting these things, so you can move around in your phase by just perturbing the Hamiltonian.
And the converse is true. So if you have such an automorphism, the Hamiltonian are close in that sense. So
I think it's a subtle question. I think maybe in general, I think it's not known, but
we expect.
Yeah. So morally speaking, it should be the same. Right. So that's sort of the motivation why we would want to look at these things. So getting this alpha is what's called quasi-adiabatic continuation, depending on who you ask. Right. So that's sort of the equivalence relation that we're interested in. Of course, we want to do a classification, and so you want to find invariants of these things. And then one of them we heard about earlier from Yoshiko. That was her motivation as well. So we want to find this category of superselection sectors, right? Good. So let me say a little bit more about the kind of assumptions that we're going to do. So yeah, so maybe say yeah. Let me not say that. So the task that we want to do, and we heard about earlier this week, how we can do this is so we extract category of anions. So that's how they usually call it in this setting. Or it's really kind of like the DHR category. It's probably more familiar. Relation here from the state. So that's the first thing, and of course you want this to be invariant. So the first question is, when can we actually define this category? And for this, we need a few assumptions. So the first one that I'm going to assume, I should maybe introduce some notation first. So instead of working with states now, I'm going to work with representations. So of course we get them just from the GNS representation. Right. So the first assumption is that I'm going to make here is pi 0 is irreducible. So we start with a pure ground state. So recent work, Yoshiko, earlier this year, Yoshiko generalized some of this to cases where pi is no longer irreducible, so for mixed states. But for us, it's going to be irreducible. The second one is also one that we heard before. So which satisfies Haag duality for cones. So we have these cone-like regions like this. And just to remind you, means this. So this is the C-star algebra generator with everything inside. You can have a Neumann algebra, and I want this to be equal to A, and let's see, component. Well, actually, for our purposes, it's enough to have approximate Haag duality. And as we heard earlier, this holds for like a large class of models, basically for all the models that we know that have this kind of interesting superselection structure that we can handle. Right. Good. So that's one more that I think fits here. One more assumption that we need. And that is that I look at this algebra. I started with an irreducible representation. So because I just have a UHF algebra there, basically this is automatically a vector. I want this to be properly infinite. Right, so in quantum field theory, these would typically be type 3, but in the spin systems, they are not. That's not always the case. So actually, in many interesting examples, it would be like a type 2 infinity or something.
And type 2-1?
Type 2-1. No, I think this one is always type 2 infinity. I think. But you can kind of restrict to sort of the edge, and you get type 1.
Factor property, where it come from?
Because from irreducibility and this one and the commitants, they generate the whole algebra, and from this you can show it's a factor.
together with actuality.
No, you need actual for this. But yeah, this really needs that this algebra and this with the C together generate a whole the big algebra. We have this.
Of course. Because it's complement. So the,
Yeah, exactly. It's just a complement.
It's just a
so this.
complement.
Yeah, this is one of these things that's easier in the
Yes.
things I think the relativity.
Yeah, if it's a ground state or a gapped Hamiltonian, that's automatic, right? Then Yoshiko proved that.
What that it's yes yeah
If it's
this
a ground state or
yes exactly yes that's indeed that was my next point. Thank you for reminding me because I almost skipped it. But yeah, so this also holds indeed if it's a ground state of yeah. And so in general, you can tensor with something to make it properly infinite. So you can tensor the whole thing with this, basically the stacking with the trivial system that I'm going to explain later. You can always guarantee that this is true. But this is kind of like an important property. So I'm not going to talk too much about proofs today. But this kind of property basically it allows you to. So we want to show like unitary equivalence of representations. Often it's easy to show that representations are quasi-equivalent, and then using this kind of showing that you have properly infinite commuters, you can leave this to every unitary equivalence. That's kind of the technical reason why we need this, and also I think we had this before in this Gravier's talk. It's also used to define like direct sums in the algebra.
You really mean the local, like the A lambdas there, or is it?
Oh yeah, sorry. Yeah, so my lambda this should be a cone.
All right.
Yeah. Otherwise it's just it's finite dimensional. Yeah. Thanks. Yeah. Sorry. Yeah. So usually I should have done this. This is kind of like a finite. So yeah. Yeah. Thanks. Yeah. So for the rest of the talk, lambda will always be a cone. Right. So yeah. So it's I already said it. So let me just write it down. So this is it's a natural assumption to make. Right. Good. So let me just recall one final result that Nico also mentioned. So under this conditions, so there is a braided C star tensor category. So let me just say it's in a C star category. Yeah, and I don't write tensor there because some terminology tensor implies like semi-symbol. That's not necessary to here. Right, so we have this braided C star category divided by 0. So this is the DHR category. So it's very similar to the one that Corey talked about, for example, earlier this week, 1 dimension higher. And this is stable. So if alpha is sufficiently local, we have this braided equivalence of braided categories. So this is, if you think again of perturbing the ground state, you get a new representation. You can do the DHR theory for this new one, and you get the same as the one you started with up to braided order equivalence. So this is really this map that Corey called the DHR of beta. Right. So yeah. So this is a nice invariant of our system. Yeah. So maybe one thing that I should mention is this doesn't really refer to the state anymore at all. So if you don't like states, you can forget about the states and just talk about the representation that has its properties. But in practice, for the physical applications, they would come from some physical systems that you. Right. And maybe another thing that I should say. So this is right. So this is just an existence result. It basically tells you can do the whole DHR machinery. You have to do a bit more work because you have this not strict target duality, but otherwise the ideas are quite similar. So, but what we can actually do, we can actually compute delta by 0 for large class of models. Right. So I did this in my PhD thesis already a while ago for the Tor code. So that's basically the simplest model that way you should get something interesting. With generalize this to a Bigin, so-called the Bigin quantum double and the non-Bigin one. And so in a recent work in progress, by Alex Bols and Boris Kier. I believe they do this for all stringnet models or some all Raven-man stringnet, and so that's what I believe.
The definition of the category, you assume that the object finite index or is a consequent?
No, so here in the category, I don't assume finite index.
Just take everything.
No. So yeah, so in these models here, for the irreducible, you can find what the irreducibles are, and you know, and for these you can explicitly define a conjugate.
So you prove that, okay.
So then yeah.
Okay.
But yeah, no, in general, so this works without assuming anything. But of course, if you restrict to, and I will do this later, if you restrict to sort of the finite subcategory for everything that has like a dual, you can get like a more structure. Yeah, so you don't need it to define the very. But yeah, that's an important part in this is really showing that you kind of like all the irreducible objects, all the irreducible representations in there. Right.
This invertibility condition, you will explain. So it's
I will get to the invertibility soon. Right. So maybe just for later. Let me just briefly recall. So what are actually the objects in my category? And these are the representations. So so these are representations. Phi from A to B of H, for some H. And from pi, of course, such that the well-known superselection criterion holds. Namely, if I restrict consistent. If I restrict my representation to observables outside outside the cone, I get something that's unitary equivalent to the vacuum representation. But that's the simple selection criterion. Right. So maybe if you know a little bit about DHR theory, you'll see why so we are in 2 dimensions here. So there the cones are kind of interesting because you get like a non-trivial grading. Well, potentially non-trivial grading. But yeah, so that these are kind of the objects, but of course you do the standard DHR approach, where instead of working with representations, you work with endomorphisms of a certain algebra. So it's not quite the endomorphism of A, but some slightly larger algebra. But that's kind of like the whole trick.
Is this equivalence of categories for sufficiently small alpha? Is that just given then by composition with alpha?
It's slightly more work. I mean, in the end, yes, but it's not completely straightforward because this alpha is an automorphism of the C-star algebra. And if you look at the DHR category, so many of these things they live in kind of a Neumann algebras that you get from the C-star algebra. So it's not immediately obvious that that's yeah. So you need to do a bit more work, which Yoshiko has done to show how it works, but essentially that's the idea. Right. So yeah, good. So yeah, so that's this gives this whatever the theorem. Right. So yeah, as I said, you can actually compute this for a large class of models where you get interesting results. But as I said in the beginning of the talk, I was well, the project was initially motivated by this invertible phases where we should have like a trivial supersection category. So so let's see how that comes in here. So when can we actually find conditions where this delta is actually trivial? Right. So I have to define something called a long-range entanglement. So if you go in the physics literature, you'll see that the claims that this existence of these anyons is due to a long-range entanglement in the ground state. So let me give a precise definition of what I mean with this. So first, going to just to look at very simple definition. So I look at the state. So this is called a product state. With respect to some cone, if omega is of this form. Right, so it's vector has a tensor product of something acting on the cone and something outside the cone. So there's no correlations in the state between inside the cone. Right, so that's so maybe I should say this. So typically when people talk about invertible states, when they say product state, they really mean a state that's kind of like a product with respect to each side. But for us, it's enough to just have a product with respect. Right. So I would say a state as a long-range entanglement or as a long-range entangled. Basically by saying what is not. So if there is no sufficiently local alpha such that this state is let's call them differently. So basically what this means is I cannot find a sufficiently local automorphism that changes my state into a product state.
Or some lambda.
Yeah, for some lambda. So no matter which lambda I choose, I can never find such a thing. So really, the idea is that there's entanglement between if you take a cone and then there's entanglement between the cone and outside, and I cannot get rid of this entanglement if I act kind of like open with a finite depth construct. So I have to do something like a non-local. Right. So that's for the state of long-range entanglement. So yes, as I said, the claim is you need long-range entanglement for to get an interesting superselection structure, and that's something that Yoshiko and I proved a few years ago. So let me see, where should I go? Here. Oh, wait. I just wrote this down, so you should be able to read that. So let's go here. So yeah, the theorem is essentially as follows. Oh, the paper I think was published in 22, if I remember correctly. If omega 0 has no long range entanglement, or let's say short range entangled, then if I look at this category of sectors, it's trivial in the sense that every representation in there, so as I said, we can think of these objects as representations satisfying the superselection criterion. This is going to be quasi equivalent to pi 0. But pi 0 is irreducible, so this just means that pi is like a number of copies of pi 0. Right. Good. So not go very fast. But yeah, so now at least we have a criterion.
This means invertible.
I'll get there. This is not quite invertible. So yeah. So right. So yeah. So maybe let me say one or two words about the proof. So really the idea is that right. So because now I can transform it into a product state. This implies that this cone algebra is going to be type 1 because I already have a product composition, decomposition of my Hilbert space. And there are basically not many interesting endomorphs of type 1 vectors. That's kind of like the whole idea. Good. So yeah, so let's go to invertible phases now. So let me yeah, so I need to say a little bit more about the stacking operation, but so maybe let me first give the idea. So what we do for invertible phases, we're not requiring that the state that we start with is a product state or doesn't have long range entanglement. But what we have is now I'm going to need two copies of my basically need two different systems. So a state omega from A1 is invertible. So on the algebra, A1 is invertible if there exists some omega bar on some other system. And so what I want to do so this is let's say trivial state product with respect to some cone. Yes, maybe I should have said that. So we only need this to hold for one cone, basically because the superselection criterion will always allow us to move to this single cone. So that's kind of why that's enough. But yeah, so the invertible phase is I don't assume that this state doesn't have a long range entanglement, but it tells me if I add on another layer to my system, I will define this precisely soon, and I can find another state on there, such that on this joint system, my state is equivalent, using this equivalence before to some product state with respect to a cone. Then I call my state invertible. So let's say it, and then omega it's invertible. Right. So with what I just said, if I look at this joint system, this implies that the joint system doesn't have any non-trivial superselection type sectors. That's what my result there gives. But I want to conclude that omega itself doesn't have any non-trivial sectors. That's kind of like the idea. So let me first briefly just to get back to this picture that we want to have. So I have to define the stacking operation. So I add my system here. I'm going to try to do some fancy 3D picture, which I already see is not going to work. So let me just use a different color. Right, so I have my original system and I'm just going to add another layer of my system. So you can think of them as sandwich 2 layers on top. And that's going to be my new system. So the algebra of this is going to be then like so let's call the observable algebras of each of them A1 and A2 for the different layers. And then of course the local observable there are just going to be the tensor product. So yeah, my notation is not completely consistent, but it's clear enough. Okay, so I've been writing the subscript S on this tensor product already a few times. So let me now explain why do I do that. It's just to distinguish, that's going to be useful later on. This is really a tensor product between the 2 different layers. So it's the usual tensor product, in this case of finite dimensional matrix algebras. But the tensor product without the S basically means I am within a single layer and I take tensor products for algebras. If I write this S there, I have something that lives on different layers. It's just easier to keep track of these things, but they're all the same with the same tensor product. Right.
How do you eliminate the, I mean, the DHR physically? What is the intuition that just by tensoring? I mean, it's strange, no? Normally, one do the cross product to eliminate DHR, no? Not the tensor product, which at best will add 0 more, but not eliminate.
So that's right. So it doesn't. That's what I'm going to show. But I mean, we want to show that so the goal of this thing is not to eliminate things, but we want to show that this thing actually didn't have anything to begin with, any non-trivial DHR. So I'm not claiming that if you started a theory that has a non-trivial DHR theory that you can add on something that makes it trivial. That's not what I'm claiming. But yeah, so you should really think of this as having 2 copies of the system together, and they're actually uncoupled. So if you think about these things again as a sort of ground state of local Hamiltonians, the dynamics of the joint system would be like given by something like this, right? So just uncoupled. So that's the second operation, and it's not so hard to verify that if you do that, so you can do this for some states. So this satisfies the same assumptions. We do DHR theory. Well, if I could do the DHR theory for omega 1 and omega 2, I can do it for the joint system, which is of course the check. So the natural question that we want to answer is, so how is the DHR category of this joint system related to the individual components? Right. Let's see, only 5 minutes left to tell you the answer. Fortunately, the answer is exactly what you would expect it to be. So I guess you can already write down the theorem. So let me just do that. And then maybe say a little bit. So maybe one thing that's maybe that you already can maybe believe from this thing is that if you start with a superselection sector from this system, that's from one of the systems, and you just tensor it with the vacuum on the other side, you get a sector of the joint system. So it's very easy to create sectors of the joint systems. And if they start with something non-trivial, you can show that the result is also going to be non-trivial. So in this in particular already answers this invertibility question, right? So we know that this joint system has no superselection sectors, no non-trivial ones. If omega did have non-trivial sectors, then we would have non-trivial sectors of the joint system. So this implies that omega does not have any non-trivial sectors. So that answers our question about invertibility. But you can say a bit more. So let me just first state the theorem, and then I say maybe a few words about the kind of proof. So erase this. So yeah, so this is of course something that's also done quite a bit in this structure of theory of conformal nets, where you take with two conformal nets, or let's say the left and the right moves, and you take tensor products and you look at the charge sectors. Okay. So what's the theorem? So let me, I'll explain what this F is in a second. So change my notation halfway my notes. Right. So if we have that every called rho1 in delta by 0 factorial is such that sorry, rho1 of A1 is type 1. Right, so let me explain this theorem in the last 2 minutes that I have. So what I'm doing here is, so now I restrict here to the finite superselection sectors, which are the ones for which you can define a conjugate. I don't think it's really necessary. It's just it's kind of the green product of categories. So usually you work with semi-simple categories. So we didn't really bother yet to sort of generalize this, but yeah.
Type 1 algebra.
So yeah, so what the extra condition that I need to assume is that so let's say for the first sector, what I want is that if I have a superselection sector that satisfies the superselection criterion for y1 and this factorial, then I want that it generates a type 1 vector. Right, so I don't need this to be true for any representation of A, only the ones that satisfy the superselection criterion. So that's an extra condition. But if I have that, I get basically the result that you expect. You would get, yeah.
What is the subscript on the A? Is there no subscript?
Yeah, this is an A1. So I have now two algebras. So the one layer I call A1 and the other layer I call A2. The observability. So this is just a sector for one of the layers, and I want all of them to have this type 1 property. Right. So yeah. So that of course begs the question. Now, what about this? Why is this going to be true in our models? And the answer is yeah. So this that's the other theorem. So the type 1 property. So maybe I should say this here. So this really comes from from this Kawagashi-Rongo-Muger paper for conformal field theory, where they have like a similar condition. That's our proof is it's very much based on that. Make some changes because of technical situations. Right. So when is this satisfied? Is satisfied when first there's two conditions. There are at most countably many irreducible superselection sectors. So yes, I think in this context, usually we work with moderate tensor categories, so they are finite, but so this is a reasonable context. In continuum cases, you can make models that violate this, but we say not too much of that. And the second one is we need the approximate split property. So we heard about the split property already before. We are in a discrete system here, so we need something slightly different. Basically, you have a cone here, λ1. You have some slightly bigger cone, and this distance needs to be sort of big enough. It depends on the model. And so you get an inclusion of Neumann algebras, and you just want that there's some type 1 factor sitting in between there. And the other thing that we show in this paper, that this approximate split property also holds if you have kind of like a strict form of the area at all. So that's it also holds in this very wide class of models. Yeah, so my time is up 2 minutes ago, so it's a good moment to stop. Thank you very much.